Now, this problem is my favorite problem on the test because it involves a few topics that we've already covered, and you have to now apply that to the solution of this problem. The problem begins, it's a momentum problem, because if you look here, it says a mass of 2 kilograms is sliding along a frictionless horizontal surface with a speed of 5 meters per second when it collides inelastically with a 3 kilogram block that's attached to a spring, as the drawing built below shows. If the spring compresses a distance of 0.4 meters, what's the force constant of the spring? So what's the force constant, which is the spring constant of the spring? So the beginning of this problem is I need to know what the velocity is to begin with when the mass when the 2 kilogram hits the 3 kilogram. So remember, going back to momentum, we had the law of conservation of momentum. m1v1 plus m2v2 equal, in an elastic collision, we're going to have the two masses combined at some common final velocity. And I know that the 3 kilogram mass is not moving to begin with. And since I'm solving for v prime is going to equal, what I'm doing here is I'm taking that and then I'm dividing by that, and that would equal v prime. So it's going to be m1 v1 divided by m1 plus m2. And if I put in the numbers, we're going to have 2 kilograms times 5 meters per second divided by, if I add up 2 and 3, so look, I've got, that's 2 kilograms and that's 3 kilograms. So 2 plus 3 is going to equal 5 kilograms. And you can see that actually the 5s would cancel out, the kilograms would cancel out, and I end up getting that my answer is going to be 2 meters per second. So after the collision, we're now going to have 5 kilograms moving at 2 meters per second. So now that I know that energy is conserved in this problem. So if energy is conserved, then I know that the amount of energy it has to begin with, which is all kinetic, is all going to be converted to elastic potential energy when it's stretched 0.4 meters. So I know that I can say that the original kinetic energy is going to equal the final potential energy, and that final potential energy will all be in the form of elastic potential energy because we're on a horizontal surface, so there's no gravitational potential energy. And so I can just say that 1/2 m VO squared, and we just solved for that VO, is going to equal 1/2 K X squared. I don't need to put A because I don't know whether that's, well, I mean, if that's how much it's stretching, then it really would also equal the amplitude, because once it reaches there, all of its energy will be elastic, and then it will start oscillating back and forth with an amplitude of 0.4. So we want the K. What's the force constant K? Well, let's, again, multiply through by 2, gets rid of that. If I want K, all I have to do is move the X squared to the other side, and then I have it solve for K. And I know all those numbers. So I'm going to get K is going to equal m VO squared divided by X squared. So I have all those numbers. I can just plug them all in, and I'll get my K. So the mass, now be careful though, the mass is the combined mass, because they're now stuck together. So it's going to be 5 kilograms that's oscillating back and forth, not 2. So I'm going to use 5 kilograms times the velocity, which is 2 meters per second squared. And that's all going to be divided by 0.4 meters squared. And I will get for my units with what I have up here. I've got kilogram meter squared per second squared divided by meter squared. I'm going to get newtons per meter as my unit. and that ends up equaling 125 newtons per meter. Now I saw somebody did this problem, and what they did was, instead of solving it the way I did, they solved it based on the force that would be slowing the object down between here and here, and they did it like a straight line motion problem that they did, like they wrote that the original velocity is 2, and then final would be 0, the displacement, the s, would be 0.4, and they figured out the a. Like they did it that way, like to figure out the a. The mistake, but they got it wrong, because the mistake that they made was they used as the force what would be the force when it's fully stretched. And remember, it goes from 0 to that number, so you have to take half that. If you want to use the force in a problem like this, you have to take the average force. And when something is stretched, it initially, there's no force on it, and when it's fully stretched, whatever that force is that has it stretched, let's say 2 meters, that's the maximum force. So it goes from 0 to the maximum. The average would be half of that, because it does go up proportionally, because it goes up with the position. So it's directly proportional to how much it's being stretched. If I get 2 newtons for stretching at 1 meter, then I'm going to get 4 newtons if I stretch at 2 meters. I'm going to get 6 newtons if I stretch at 3 meters. So it's proportional.